Okay, super. So what we saw in the last class is so we said how do you actually prove an example, correct? Right. So we define this transitive flexible closure, um, and we use that relation to say that oh, you can start from this state and end up with this state by applying transitive reflexive closure on this step relation, which tells you how to step through factorial. And you can do that by repeatedly applying e-constructor, essentially, which is what we've done here. Um, and let's, sorry, I have this in the wrong window. So what I was saying, which you weren't able to see earlier, is that we proved the factorial 3 auto, um, which we proved by just saying we can start from this state and apply multiple steps of fact step, right, and get to answer is 6 by using this transitive reflexive closure property. And what we said is that you can do it explicitly by carefully applying the constructors one by one. And luckily in this case, right, so it turns out that whichever constructor you can actually unify with is the constructor that you actually want. So so repeating e-constructor application, which just picks the first constructor that unifies, right? Just makes the proof go through. So this is all fine, right? But the whole point is we are adding up to saying, how do we prove that this transition system is actually going to match the behavior of what you would observe in a real factorial program? So let's switch to the slides for a bit. Okay, so can I close the sidebar? Okay. And can I close this notes? Navigator. Anyway, so we define transitive flexible closure, right? And one thing we can do is we can also define the reachable states of a transition system. So given a transition system that has a set of states, initial state, and this step relation, we can say, I mean, this is sort of an intuitive definition, right? We can say that a state S is reachable if and only if there exists an S0 that is part of the initial state, and you can take multiple steps from S0 to S, right? And that is what we call as a reachable state. Yeah, and why do we need this reachability? It gives us an intuitive definition of it is a useful tool in order to describe the intuitive correctness property that we want for this factorial, right? Which is that take this factorial system, right? This F system, and for any state S, if S happens to be the final state, F omega is the set of all final states, right? Then S has to be answer is n0 factorial, assuming that n0 is the initial state, right? So what we say is that given the initial state starts at n0, if you ever reach a state which is a final state, then the value that is there is going to be n factorial, and this factorial is defined by this in Coq, right? This is defined in we take the functional definition of the factorial as the definition for this exclamation, essentially. And this is how we are relating this transition system, right? Where we have states and steps in the transition system to this functional definition, right? Again, to remind you, right? So this all seems too much of a pain. In order to prove the correctness of factorial, we know we can do correctness of factorial just by this definition, functional definition. And the point of doing this is that we are going to use this repeatedly in the upcoming lectures, where we can do much more interesting things like concurrency and infinite programs and so on. Anyway, so we can prove this property in an ad hoc fashion. Okay, so that's true. We can do that. We have learned enough to enough of Coq mechanization in order to be able to do that. But there is this general notion of invariance that is quite helpful in order to reason about these systems which have this iterative nature, right? In practice, so the iteration here comes from this repeated application of steps. And whenever you have this repeated application and you want to reason about a system which has repeated application, right? This is true with while loops. This is true with recursive functions and so on. We sort of try to come up with these invariants. And what is an invariant? Invariant is some property that is true at the start of the program, right? That is true at start of some iterative structure that you have, right? Holds true at every step of the iteration, and it is also true when the iteration completes, right? And yeah, invariant is a property of a program that starts true and stays true. So what is the notion of an invariant for a transition system, given that the transition system that we described also has this transitive flexive closure, right? How can we define that? An invariant of a transition system is a property that is always true in all of the system's reachable states, right? So initial state is also part of the reachable state, and every state that is reachable is also, every state that is also reachable should satisfy a property, and such a property is called as an invariant, right? And one nice way of defining that formally is just by defining the invariant as a subset of states. So this may seem odd at the beginning, but it's a useful way of defining invariance. So consider that you have a transition system, which is a set of states, initial state, and the step function. And R is a set of all reachable states, right? So R is going to be a subset of S, right? Because S describes like all of the possible states. We describe invariant as a subset of S, right? Such that invariant, I mean, it is if and only if all the reachable states are in fact a subset of this invariant, right? So R subset of I subset of S is the relation. And the way to reconcile this thought process is that you might have some property, right, which holds precisely on all of the reachable states. You might hold some property. You have a set of states. The set of states in our system, right, is these two, right? I can I can always say here is an invariant, right? A silly invariant which holds true. I can say that on all the states, right? And the two states are these two. So I'll do case analysis. If the state is answer is, then n is going to be greater than or equal to 0, right? That is a true property. But if it is with accumulator, then this n and this n is also going to be greater than or equal to 0. This is an invariant, right? This is an invariant because this is precisely describing all of the states. So this is the invariant that I defined here, I, is equal to S, because the set of all states that I described as part of this invariant is actually equal to S. But you can be a little bit more maybe precise. Let's try something else, right? We know that factorial of 0 is going to be 1, right? So this n is never going to be 0, even though it's a natural number, right? So another invariant that I can write is invariant is just a property, right? So I can just say if it is with accumulator, I'm defining a new invariant, and I'm defining it by case analysis, right? If it is a with accumulator, the state is with accumulator, the invariant is just true. I'm not saying anything about the invariant. I'm just saying the invariant holds. If it is answer is, right, this n is going to be greater than 0, right? So this holds true for the system because wherever you start with, we always have the answer for a factorial to be greater than or equal to 1. So I am defining an invariant now, which is going to be a subset of the states, right? S, this set that I'm defining as part of the invariant, is going to be a subset of S because it doesn't particularly include answer is 0. That is part of S, but not part of the invariant that I just defined. And that is also an invariant. I mean, even though it's sort of not saying anything about factorial, talking anything about the factorial, it is still an invariant over this system, right? And the key idea that we want to do is that we want to pick an invariant strong enough to prove the property that we want to do. And the property that we want to prove here is this factorial, right? I want to show that whenever I reach a final state, the property that I want to show is um, the result is going to be factorial of the initial value. So neither of the invariants that I told you is going to be useful in proving this property. But you can, in fact, pick invariants which will help you prove this property. And that is what we are going to do in this, right? And that is the way to reconcile this definition that invariant, right? Mathematically, a property of states is just a set of states. The invariant that I describe is going to define a set of all states. And as long as this invariant is a superset of R, right, at least captures all of the reachable states, then we call that as an invariant for the transition system. Right? Let's make this more concrete, right? So I've defined at a high level what these are. Now we will sort of go into Coq and we'll actually prove how this is going to work. Firstly, I've been using this transition system all the time, right? We have this syntax for transition system, which I said set of all state, initial state, and the step function. Let's make it a first class thing in Coq also. So in Coq, you can define records, just like you can define records in OCaml. We can define records in Coq. And um, the syntax for records is that you use this curly braces, right? And you give it a name. Every field has a name, right? And every field has a type as well, right? And this particular record is also, because Coq has advanced type system, you can sort of, these records can take parameters. And the parameter here is sort of fixing the type of this record. So the way to read this is I'm defining a record for transition systems that is parameterized by the state, right? You can define different transition systems, and each of these transition systems is defined on a particular type of state. The way to think about this is TRSys is defining a universe of transition systems, each of which is indexed by a particular state. So there will be one state for, say, factorial, one state for something else, say Fibonacci, and so on. But for what do we expect for all of this? There has to be an initial state, right? Initial set of states. So the way to again read this is relational way of looking at it, right? When I say this is a function, this looks like a function, right? From state to prop, it's a unary relation, right? And a unary relation is just a set of states here. And step is a binary relation that relates one state to another state, right? And that is how we define transition systems. This is just the syntax for records. It comes in handy whenever we tend to use systems later. So here is the definition of the factorial system. So we've been looking at factorial so far. So here is the definition of factorial system. So the thing that we are going to define is the transition system on factorial state, right? And here's the definition of factorial system. And because this is again indexed by the original input, so this definition is also indexed by the original input, right? So this is sort of like a function definition. If you want to define the factorial system, give me the original input. What I will return is the factorial system, right? And for using records, if you want to actually create record values in Coq, again, this is some syntax, right? You have to use curly braces bar and bar close curly braces for the values. So observe that this is different from OCaml, right? In OCaml, we still use just the curly braces. So for types, you have to use just the curly braces. For values, record values, you use curly braces bar. That's just the syntax. And again, um, if you want to actually represent the values in for each of the fields, you have to use colon equals. Um, Again, equality is taken over by the propositional equality in Quark, so that's why we have to use colon equals. But anyway, apart from the syntax, right, what are we saying? We know what the initial state is. We have this definition for fact in it, which is parameterized by original input, right? Just to recall fact in it, where is it? So this is fact in it, right? It is parameterized by the original input, and what you get is a fact state to prop, which is the type that we expect for the initial state. And then similarly, we have the fact step, which is a state to state to prop. So we have defined a factorial system, and we defined a reachable set here, right? Reachable states is a set of all states that can be reached from the initial state. We can define an inductive in order to describe the set of all reachable states. It's a useful general notion for transition systems. And the way to read this is that there is a implicit parameter called state. Given a system, right? It is sort of relating some state. The way to read this is reachability is a relation that relates a given system to a state. And what the property it says is that this state is reachable in this system, right? And the way we define it is through an inductive. And oftentimes we define it using inductive so that um, I mean, you can define it as a recursive function, right? Um, if you had actually started out defining everything as a recursive function, we define it as inductives just because inductives are much more nicer to actually use in proofs, just like we saw in the logical programming lecture, right? So inductives are sort of give you proofs for free. So what does it actually say? This reachable is a constructor, but really what it says is that if a system, if the state st is reachable in the system, then for all state st0, so for some state st0, where st0 is an initial state, right? This is another precondition that has to hold, and you should be able to reach by taking multiple steps from st0 to st, right? And that is what we define as a reachable state. So the reason for defining it as an inductive, which will become apparent later, is that sometimes we just want to say, I want to show that ST is reachable in the system. So I will just apply this constructor directly as a proof step, and I will have to prove these two sub goals, right? These two properties as well. I have to show that from some initial state, I can reach this ST, for which I am showing that this reachability property holds. So you can also read it in forward direction, right? That is a backward reading. The forward direction is that for any state ST, right? For all ST0, if ST0 is initial state and ST is reachable from ST0 by taking multiple steps, then we say that in that system, the state ST is a reachable state. Okay, so that is the definition of reachable. So we've defined reachability. Okay, so now we saw this idea of invariance, right? We wanted to use this property as a instead of proving it in an ad hoc way, I want to actually use this idea of invariance. So for invariance, what we are going to do is we are going to look at three ideas essentially. So how do you define an invariant? Like what are invariants? For that, we are going to see a definition called invariant for, right? How do you use the invariant to prove some property on the transition system? So we will see this definition called use invariant, right? And again, so the third thing that you want to do is you have a transition system, right? And you want to say, oh, I can come up with a property. I want to first establish that that property is in fact an invariant for the transition system. So one example is that we said whenever we see answer is n is greater than 0, and whenever we see the width accumulator, it is just true. How do you know, how do you convince Coq that the property that I just defined is in fact an invariant, right? For that, we have to explicitly establish that a particular invariant holds on a transition system, which means that the invariant is true on all the reachable states. It can be true on other states as well, but it has to be at least true on all of the reachable states. And for that, the way to establish that is by induction, right? You say that it holds on the initial state, and then assuming that it holds on some state, we say that it must hold on, we will prove that it must hold on the next state. Uh, Induction is the way to do it. These transition systems are inductive, right? You can take one step and then you can take several steps. This is precisely how we will establish invariance for a transition system. And for this, we will use something called invariant induction. So that will allow you to take some property, right, and establish that as an invariant on a transition system, right? So I will. So what I will do is I will not go through the proofs for this in detail. At this point, what I expect is that you can deconstruct the proof by yourself. Again, this is not important. If it is important, I would have gone through. So the intuition for what these provide, this use invariant provides an invariant induction is important, but the proof for what these things are is not important. So I will not go through in detail, but the proofs themselves are very small, so you can do it by yourself. The first thing is, what does it mean, right, to state that some invariant is an invariant for a system? As I said, if you want to say that some property which is an invariant, right? Invariant is defined as some state to a prop, right? And you can read it as invariant is some property that defines a set of states, right? Or the yeah, that's basically the reading here. So invariant is defining a set of states, right? And when can you say that this invariant is a invariant for a transition system that is cis? So um, so essentially, what we want to show is that we can define invariant for as for all states S, right? If S is an initial state in the transition system, right, and there exists some S prime, right, for all S prime, that you can take by applying 0 or more steps from S to S prime. Again, recall that this transfer reflexive closure also allows 0 steps, right? Because it's also reflexive. So S prime could be S as well. This S prime, right? This invariant should hold on this S prime. So the intuitive reading of this is that the invariant must hold on the initial state, right? The invariant must hold on every step that is reachable from every state that is reachable from any of these initial states. And that is the definition of invariant. I mean, this is what we said invariant is. And here we are just defining it, right? And again, whenever you see a star, it is 0 or more steps, right? So keep that in the back of the mind. Okay. And yeah, okay. So now, again, we are going to use a lemma to prove and use invariant prime. But what is a use invariant? How do we actually use an invariant, right? So why do we want to use an invariant? I want to prove some property, right? And whenever I see, say, an invariant is, I want to use that property, right? And what does that mean? The intuitive reading is that for all systems, right? Assume that a sys is a transition system, right? And I have some invariant, right? And I have some state S. I want to show that invariant holds on S. Oops. Invariant holds on S. So what do I need to do, right? I have the system, I have the invariant, I have some state S on which I want to show that the invariant holds. You can show this by showing that S is a reachable state in the system, and this invariant is an invariant for the system. Right? This is basically repeating the definition, but the intuition is important. Whenever you want to prove that invariant holds on S on some system, one way to prove it, right, is to say that in the system, S is a reachable state, and this invariant is in fact a invariant for the system. So that is how we might use an invariant. So proof I'm going to skip. You can analyze that in your own time. And so that is actually showing that an invariant holds on S, right? And the other flip side of that is that how do you actually establish an invariant? So you have a transition system. You can come up with arbitrary property, right? I can just say the invariant is false. This invariant does not hold on any system, because every system this fails. But I might come up with interesting invariants. How do I establish that this particular invariant that I come up with is in fact an invariant for a transition system? We use induction, right? So the reading of this is here, right? Given a sys, which is a transition system, right? I want, and given an invariant, which is which is sort of defining a set of states, I want to show that this invariant is an invariant for the transition system, right? How do I show that? The reading is that you first show that for all S, which are all initial states of the transition system, this invariant must hold on that state. Invariant holds on all of the initial states, right? And for all states on which the invariant holds, right? So this is the inductive step, right? That's the base case. This is the inductive step. Assume that you pick a state on which the invariant holds, and you can take a single step from S to S prime. So that's the next step, and you have to show that the invariant holds on S prime as well. So this is the inductive step, right? In order to show that invariant holds on an arbitrary S prime, you assume that it holds on S, and S is precisely the previous step for S prime, and that's the inductive step. If we can show both of these, then you can show that then it means that this invariant is an invariant for the system, right? So this is how we actually establish an invariant. So there are two useful things here, right? So in order to say prove some property on a transition system, we will first have to come up with an invariant. We will use invariant induction to actually show that the property that we have come up with is invariant on this transition system. And in order to prove certain states preserve certain invariants, so we can use the invariant theorem. So we will use that later in the proof. Okay, so this is all like tools for reasoning about transition system using invariants. But let's actually dive down and look at example, right? Earlier we had come up with two silly invariants, but I really want to have an invariant with which I can prove that the result of making transitions in this transition system which encodes factorial, the answer is going to be related to this functional definition of factorial, right? So I'm going to come up with an invariant. So here is the invariant that I'm going to come up with, right? So assume that original input is the input, right? And ST is the fact state, right? And so here is the definition of invariant. So invariant is defining a set of states, right? So it's defined as if the state ST is answer is ans, then it must be the case that ans is equal to the fact of original input. This fact definition comes from the functional definition of factorial. So we are sort of establishing, right, a link between the invariant that we are describing on the transition system and the functional definition of factorial, right? So that is the last step, right? So we establish this property. This is sort of intuitively where we want to get to, right? And for the inductive steps, right, everywhere else, when you see with accumulator and accumulator, how does it relate to the fact definition? So if you took the factorial of original input, right, that must be equal to the factorial of whatever n is at that step multiplied by this accumulator, which is precisely the definition of how we apply this factorial function. But this sort of now in both of these states relates factorial to those states. Okay, so I've just given some definition. Intuitively, this holds true, but I haven't actually shown the proof that this is a good invariant on the system. I have to show that this property actually holds on all of the reachable states. And in order to establish that, we will use invariant induction. I just came up with this property, right? I haven't actually shown that this is an invariant for the system. So here I have this theorem called factorial OK. And all I'm trying to do is to say that this fact invariant, right? The invariant that I've come up with here, this fact invariant on this original input is the invariant for the factorial system, which is also parameterized by this original input. Okay, so I'm establishing that fact invariant is a good invariant on the system. Okay, whether it is good enough to prove the final property is a secondary question. I'm just establishing that this is in fact an invariant. Okay, so for now, for this, let's actually go through step by step, right? So okay, so I have this property, so I'm going to first apply simplification. And the simplify, right? So this is from the, actually all I'm doing is intros, but simplify also does the work for me. I just want to show that simplify is from the frap library. It does a lot more than just the simple tactic that we had seen in the earlier examples, right? Earlier lectures. So simplify just moves it to the original input to the assumption. And so I want to establish that this particular property is an invariant for this system. And we are going to do that by induction, right? And this is what we said earlier. So I'm going to establish this property by applying induction. And so if you sort of look at this, right? So the the actual thing that we have here in this theorem is that the property that shows when you can establish some invariant is an invariant for a system, and the preconditions for that are the base cases and inductive cases. So I'm going to apply invariant induction, just like we did applying induction on structures that we have defined, right? Inductive structures that we've defined. This is also a form of applying induction, but this is very explicit, right? We are not using inductive types. We are sort of, we've defined what it is to apply invariant induction, and we are going to just call that. So just like applying induction on, say, lists, we have to prove both the inductive case and the base case. So we will end up with two sub-goals when I do this, right? So I'm applying invariant induction and simplification, right? So I end up with two subcases, right? One is the base case, another is the inductive case. So, okay, so I have to show that assuming that H is a initial state, this S is an initial state, this invariant holds on S, right? Whatever fact invariant that I've written down holds on the initial state. Right? So what do we know about fact init? So if you sort of go back to definition of fact init, right? Where is fact init? Fact init is here. So it's an inductive type, right? And fact init says that if you build a value of this type, then the only way you can actually have the state is it has to be with accumulator original input 1, right? That is the only possible state that you can have, right? Fact init, original input, and the only possible value that you could have is this one. And here we have some arbitrary fact state, But we know that given that this property fact init holds, right? This has to be of this structure. And because we've defined this as an inductive type, we can use this tactic called invert. You've seen this previously, but invert is a very powerful tactic. We will use this often, all the time. But invert, you can sort of intuitively understand as whatever is obviously true about a particular inductive type, it sort of makes it obvious, right? So what did we know about this? Because this fact init holds on S must be with the accumulator original input 1. This is what we saw in that inductive type. And when you do inversion, the invert on H, that is precisely the fact you will learn. So when you invert on H, we magically learn that this S, right, this S that appears here, that has been replaced with accumulator original input 1. So there is, because we've defined that as an inductive type, and we know that that has a particular structure, inversion, all it does is it sort of destructs and then says what are all the facts that I can learn from that definition, and it has just substituted that here. So it knows that S, the only possible value for S is with accumulator original input 1, and that has been substituted. And fact invariant is just a definition, right? So we can simplify. So when you simplify, um, sorry, where is the fact invariant? Fact invariant is here, right? With accumulator and accumulator, right? It goes through this case and does the substitutions, and you end up with proving something that looks like this, which is what you have here, right? And this is obviously true, right? So this is some term equals some term multiplied by 1, and that goes through with ring. So by ring, we've established that. So far what we've done is we've established that on the base case, on this transition system, fact invariant holds, right? That is all we've done. We have to do the same on the inductive step as well. So I have to show that on some S prime, fact invariant holds, assuming that S is a fact state and fact invariant holds on S, and you can take a step from S to S prime, right? This is the inductive step. So there are basically two ways to take a step, right? There is a one way which is a step from the with accumulator to the answer state, and the other step is from a with accumulator to a with accumulator. So those are the only two possible kinds of steps, and that we learn by inverting this fact H0. So when you invert H0, you will see two subgoals that precisely correspond to those two subgoals. Okay, those two kinds of steps. So yeah, so there is H0 here, which I invert, and I know that there are two steps, and these two subgoals are obtained directly from for each of those two kinds of steps that I can take. So if you sort of see this, right, the hypothesis says that assume that the previous state, right, which is with accumulator, 0 accumulator, right, fact invariant holds on this state, and the result of that state is going to be answer is accumulator, right? And I want to show that fact invariant holds on this state, assuming this hypothesis, right? So if you do simplification, it has simplified all of the terms, right? Now observe that the previous step, the induction hypothesis, actually is useful for proving this one. So this is just the same as this one, except you have a plus 0 here. And linear arithmetic knows how to also apply the assumptions in a useful way. So we use linear arithmetic here, but you can also do it explicitly, but that's fine. Similarly, right, assume that fact invariant holds on this step, and the way you go from this step to the next step in the transition system is this becomes n, and accumulator becomes accumulator times n plus 1, right? So assuming this holds on, fact invariant holds on this state, I have to show that fact invariant holds on the resultant state. So again, we just simplify. and we rewrite for the term fact invariant original input, the right hand side term, right? So if you do that, you will see that this is a linear combination of just multiplications, right? And ring tactic knows how to discharge this. So we call ring, and we're done. So what have we done? So we have established that this invariant that we have written down is in fact an invariant for the transition system that we have defined earlier, which captures the factorial. Okay, so that's really what we've done so far. And yeah, so as a corollary, right? So you can also define it as for all original input and states, if S is a reachable state in this factorial system, then this fact invariant holds on S, right? This is directly true because of how we've established this fact invariant. So you simplify. Here I want to show that on S, this fact invariant holds, right? And here is where I apply use invariant. Okay, so use invariant is used to show that a particular invariant holds on a given state, right? So if you use invariant, I will have to show that there exists an invariant, right, for a system. So here is the invariant, and the system is in fact the factorial system, right? I will first show that this particular invariant that we've defined is an invariant for the system. It's a unification variable, but we will unify it with the fact invariant OK, which is what we've defined here, right? Sorry, here fact invariant OK. So we will say that we will directly appeal to this, right? So that this question mark sys gets filled by this factorial system. So we've established that that is an invariant, and we have to show that this is reachable, right? So S is reachable in the system, which is again just part of the assumption, right? So that just goes through. So this is just a corollary, right? So we are just saying that on all of the reachable states in this transition system, the fact invariant holds. So we've done that. So now we actually get to do the interesting thing, right? I could have established any invariant at all. But the point is, I've chosen that invariant to prove the property that this system is related to this factorial function, the mathematical representation of factorial function, right? So, so given that we've established this invariant, we can now prove it. So what are we doing here? We are actually showing that therefore any final state has the right answer. By the right answer, we are actually saying the answer is factorial of the original input. So how do we define it? For all original states and original inputs and states, yes, right? If S is the final state, right, and fact invariant holds on S, it must if it is actually the if it is actually on the factorial system, but we'll come back to that. Then S must be answer is, because that is how we define the final state, and the value that is precisely in answer is the factorial of original input, right? So so we do the introductions, we invert fact final just to know that the only possible state that is a final state is the answer is. That is what we will learn. So observe that this S and this S will be replaced by answer is, right? Answer is ans, right? And if you simplify, you'll just see that we we got this from here, right? We assume that the factorial invariant holds. So if you simplify that, because of how we define the invariant, we get the fact that factorial of original input equals answer, and just by doing this rewrite, we will get so you can replace this term with ans here, right? And they will be trivially true. But equality does all of the simplification for us. So we just call equality, and that goes through, right? So, okay, so that's that. But we still haven't said anything about the factorial system here. So let's bring that into play, right? So for any reachable state in this factorial system, right? If S is the final state, then the final state has the right answer. So that is also a simple proof. So we do simplification. We appeal directly to this lemma that we proved here. I want to show that S equals answer is fact original input, S equals answer is original input. We apply that. I have to show that fact final of S and fact invariant original input S. Both of these are, I mean, one of this is directly the assumption, right? So assumption makes it go through. And for this fact invariant original input S, I can appeal to fact invariant always, which is the corollary that I proved, right? Which is that for every reachable state, this factorial invariant holds. So I'm going to appeal to that, which the precondition is that I have to show that S is a reachable state in the system, which is again an assumption here, right? So assumption makes it go through. So that's basically it, right? So what we've done is that we have shown that if you sort of pick this factorial system, right, and you say, okay, in this factorial system, I make all of the transitions and I reach the final state, right? The final state is in fact has the correct answer, which is what we proved. Now using this invariant way of proving things. Um, yeah, so that's essentially how we will sort of establish proofs on these transition systems. We will see one more example tomorrow. I think I'll actually stop here. I won't. I want these ideas to sink in. So we will see a more complicated system. Actually, we'll see a multi-threaded program and how to use transition systems on for proving properties about multi-threaded programs. It is actually quite powerful, this way of reasoning about transition systems. It will be very tedious in the next step because we are explicitly encoding all of the transition systems. But what we will do in the next lecture is we will study how to define small languages and then automatically relate it, not automatically, relate that to transition systems that are possible from interpreting those languages. Okay. So there is a lot in this lecture, I know. So what I want you to do is digest this, right, and come back with questions, right, and then we will sort of address all the questions, and then we'll make sure that you understand the material, and then move on. So, um, so we had one compensating class for the missed week last Saturday, right? Would you be available this Saturday? Because I have all of you here. If not, we can schedule it later. But are you available this Saturday, everyone? Shashin, Sriram, are you available? Okay, super. How about others?
Yes, sir, we are available.
Okay. Vishnu, Akash. Yeah, okay. Deepali is available. Okay, Akash is not. Okay, that's fine. So, uh, yeah, okay. Okay, so that's fine. So, what do we do? So, uh, Vishnu, do you prefer not to have classes on? Okay, so you don't want to. Okay, that's fine. So that's fine. So let's let's have the class on Saturday, right? So and then Akash and Vishnu can watch the recording. Um, and please ask questions, right? So you could have, I mean, use the time to actually stop me if you don't understand something. If it's just flying over your head, you can just say, okay, can you repeat that again, right? Some of these are like very new, right? So feel free to poke me about stuff that I taught earlier. I may not have everything at the tip of my tongue, but I can sort of go back and sort of work through and find out collaboratively, right? So we can try to answer earlier things as well. Anyway, we'll have a class on
Sir,
Saturday. Yeah, Deepali.
on Saturday, is it on multi-threading?
Yeah, so this is essentially covering the rest of the stuff that we have here. So the examples, I mean, look big, but essentially, what we will do is that we are going to reason about a very small program, right? There is a lock, there is a local variable, you have a global variable. We are going to increment the global variable, right? And what we will prove is that when you run this program on two threads, you will always end up with I think if you start with the global variable as 0, you will always end up with 2. This is the property that we will end up proving. But we will prove it formally by describing a transition system. It will seem very tedious. The reasoning is very simple. We know how lock works, we know how unlock works, but this is all stuff that is in your head. So you'll sort of see um, how to convince Coq that this is in fact correct. The intuitive understanding, right? We will see how to formalize all of that understanding. It will be tedious, but the point is, once we cross this tedium, then we can lift up the level of abstraction. This is like we are sort of learning the principles from bottom up, and in the next lecture, this will be much nicer to reason about. Anyway, so okay, so we'll do this on Saturday, and I think for the rest, you can just watch the lecture, and then stop me and ask questions, right? So I think that's quite important. Anyway, so we'll stop here then, and I'll see a subset of you on Saturday morning. Then, thank you. Bye bye.